let's start. Maybe you can close the door. Okay, so today I want first of all to finish the subject that we started last week, and I don't have a lot of time to devote to it, so you will discuss it more in the tutorial next week, filling up some technical gaps, and probably we will post some kind of summary of the things that I didn't get to teaching, because this is just for your enrichment. We have to start a new subject today. Okay? לא יהיה שום דבר במבחן שלא למדתם בכיתה. Okay? Shall I repeat it again in English? Everything, the exam will only depend on what I say, or me or Sar, in class. Okay? I'm not going to ask you to learn anything on your own. Okay, so what we started discussing last time is an example of the use of mean field theory to describe a problem where the ground state is different in nature from a free particle gas. And that's the case that you have a Hamiltonian with attractive interaction. So I'm not writing everything again, but just mentioning that first of all, the single particle part is just a free electron gas, and it is expressed in terms of creation and annihilation operators for electrons. And here the psi of K is the kinetic energy epsilon of K measured relative to the Fermi energy, not with respect to zero. So this is a kind of a grand canonical version of the Hamiltonian. And because of that, the psi can be either positive or negative. And in the interaction, I'm not writing it explicitly again, but you have a model where V of Q is a constant and it is attractive. So we write it as minus V, where V is positive. So this is attractive interaction, and we're going to see that it is important. So this is the model we started from, the microscopic model, and we cannot handle it exactly, so we make an approximation, or rather what we do is we make a guess on the ground state. So we assume that there is a new ground state, which I call BCS state. And it is such that, unlike the situation in a free electron gas, the expectation value of a pair of annihilation operators, where K, here I remind you of a notation that we define K without a vector sign to be a combination of some momentum K vector and the spin. So minus K is reversing both the spin and the momentum. Okay? It's the time reversal partner. So usually this, I mean, if we just have a Fock state, this always vanishes because it has only annihilation operators. And when I'm writing this, this is a short notation for calculating in the new vacuum state, in the new ground state, sorry, okay? And the assumption is that this is not 0, okay? And if this is not 0, no, so this is, if you like, it's a wild guess about the nature of the ground state because it allows such expectation value. But we have to justify it in retrospect. And this is what I'm going to complete doing today. Now, under this assumption, and this is just an assumption, what we get is if we define a delta to be the interaction of V times the sum of K of this non-vanishing expectation value. Now delta is going to be non-zero under this definition. And when we replace the interaction part of the Hamiltonian by a mean field approximation, where a pair of every operators is replaced by their expectation value, just like we saw in the Hartree-Fock case, then we get an effective Hamiltonian that we call HBCS, which is an approximation for the original Hamiltonian. And we saw that we can write it in a matrix form, like that, where HK is a matrix that I will remind you shortly what it is. So first of all, here, psi K is CK, C minus K dagger, okay? It's a kind of a spinor with two components. One describes annihilation and one the creation. And H is the matrix, H of K is the matrix psi K minus psi K minus delta minus delta star. Okay, I just repeat what I showed you last time. And this is a 2x2 matrix that can be easily diagonalized. So what we saw is that we can diagonalize it by a transformation which defines new particles, or let me call them quasi-particles, and this is a Bogolyubov transformation. Okay, and it looks, let me write it like this. Okay. Write it as a matrix. This is a unitary matrix, okay, provided that UK plus VK square equals 1. Now notice that I could actually write here a more general transformation that involves complex numbers. For simplicity, I chose the coefficients to be real, but this can be easily relaxed. And therefore, if these are real numbers that obey the unitarity condition, I can actually represent them by cosine and sine of some angle. Okay, so here we can define an angle theta for each k, which may be different for each k, such that uk is a cosine and vk is the sine, and therefore this is like a rotation transformation, okay? And notice that what are these new quasi-particles? The operators gamma are superposition of annihilation and creation. So they are superpositions of electrons and holes. And there's another property that I want to mention, and that is that uk equals u minus k, and vk is minus v of minus k. Why am I saying it? I'm not sure, maybe you'll discuss it in the tutorial, so I don't have time to get to enter this, but let me give you a hint why it has to be. Okay, so there's some symmetry properties between the k and minus k. And why is that? Because you see that here, if we take just gamma k and put a dagger, gamma k dagger should be the same as this one if we replace k by minus k. So it has to be consistent, and that happens provided that you satisfy these properties. Okay? Okay, so actually, you know what? I told you that they should be real numbers. Okay, let's leave it like that. Okay, that's for real numbers, but you can make at least one of them complex, and it will not change. It will still work. Okay, so with the new gammas, we get a diagonal Hamiltonian that can be expressed as the most usual single body Hamiltonian, but with energies that equal the square root of psi k square plus delta. Okay. So, and this is the energy of the new quasi-particles above the vacuum. The reference state is 0 because we define all the energies with respect to a Fermi level. So the Fermi level is like our ground state level, and this spectrum, compared to this 0, it has a gap. Okay, it has an energy gap. So this is how it looks. This is the 0 of energy. As a function of k, we get a hyperbolic dispersion, and there is a minimum delta absolute value. Okay? Okay, so the first thing I want to do today is to discuss what is this ground state. What is this ground state that gives you a non-zero expectation value for c minus k and ck? So this BCS, how do we define it? We define it in such a way that in the new basis, in terms of the particles described by gamma, for them, for the gammas, for the quasi-particles, BCS state is a ground state. It's a vacuum. It's a vacuum state. How do we define a vacuum state? It's a state where if we apply any annihilation operator, we get 0. Okay? So, Okay, so it has to satisfy, if that is the, for that to serve like a vacuum, and for the gammas to be describing particles created above this vacuum, I have to obey that applying any gamma k on the ground state will give me 0. Okay? So this is the condition. With your permission, I'm erasing this because we already have it. Okay, so and let me also erase this because these guys are going to be here. So, okay, so gamma k has to satisfy that when I apply it on the BCS state, I get 0. Okay? Actually, now I'm sorry that I erased it, so let me just rewrite the transformation. So what is gamma k? So what I want now is to express the BCS state in terms of the original electron operators, right? We know that it's different from a Fock state. What is a Fock state? It's a product of CK daggers applied on the real vacuum and are filled up to the Fermi level. That's the Fock state. But the BCS state will probably be something different. It must be because we know that the gammas are combinations, they're linear combinations of CK and CK dagger. Okay? So if we apply it on any Fock state, I will always get something non-zero. Okay? Because either the state is occupied or not. If it's right, so I always get something non-zero. But here, I have the combination. So this is gamma. When I apply it on BCS, I must get 0. Okay? So what is it going to be? Let me make a guess. But we can easily check that it works. It's not a unique way of writing it, but it's the most appealing in terms of the interpretation. Okay, so I'm making the following guess, and we're going to prove that it obeys, that it's annihilated by all the gammas. And this is my guess. It's a product of all k of uk plus a vk. Let me just see. Yeah, k daggers acting on the vacuum. Okay? And remember, U and V are part of a unitary transformation, so the sums of their absolute value are 1. So this is like cosine theta plus sine theta. What can we say about what is the interpretation of this state? How is it different from a Fock state?
Create a pair.
So that's right. So that's right. It actually creates a pair, but only with some finite probability. If we take the special case, let's take a special case that UK is 0. Okay? If UK is 0, then V must be 1. And then we're actually back to the Fock state, right? Because for every K, I have a product of, actually, maybe there is a normalization factor here that I don't care about, but basically, if one of these, if, of course, if V is 0, if V is 0 and U is 1, I just get the vacuum, okay?
You can explain how if U is 0, it's go to...
Yeah, so if U is 0, then V is 1, and then I just get pi k, c k, dagger, c minus k. Now, remember, this k is k vector and spin up, and this is for the same k. Now, if I take the product of all k, the product also includes k and minus k. So basically, it covers. So this acting on the vacuum basically gives you a Fock state. Okay.
But it's not a ground state.
No, it's not the ground state.
But PCS is.
No, I'm saying if we found, let me put it this way, we're shortly going to write to express these in terms of delta. In the case that delta is 0, if delta is 0, then we are back to the free gas, okay? Yes. And that's the case where UK is going to be 0, okay? But generally, for non-vanishing delta, U and V are not 1 or 0. So this is a non-trivial superposition. So what do we get? For each K, instead of just getting, creating one particle for each K, or one particle with spin up and one particle with spin down, what we are getting is that we either create a pair or nothing. And there is a superposition between them. It's like a Schrödinger cat that is either empty or full, but the full is two particles. It's a pair of particles, and not just any particles. There are two electrons with, so if you like, there's some kind of a virtual bonding between two electrons that have opposite momenta and opposite spin. Okay? Okay? So, and this pair is created, this pair is also called a Cooper pair, after Cooper, who's the C of the BCS. And the ground state is, I emphasize, it's not just that you create pairs, you create a state where for each K you have, with some probability, nothing, and some probability, a pair. Okay? That's what it is, and therefore, what can we say about the number of particles in this state? This state is not an eigenvector of the number operator because it doesn't have a well-defined number of particles, right? And notice that actually if we expand the product, because it's a product of such things, I'm going to get, and I just sum them according to, I sum the contributions according to how many particles there are. You're going to get everything from 0 to a microscopic number, okay? So it has a very, very unwell-defined particle number. However, of course, we can compute the expectation value of the number of operators, and we'll get something, okay? We'll do it in your homework. It's an easy calculation, but the result will not be just the standard, it will have actually a standard deviation. It's not a well-defined, it has some uncertainty, okay? The number of particles will have uncertainty. Okay, so that's, if you like, it's the first time we are seeing a state that you can think of it as a superposition of Fock states, which have well-defined quasi-particle, number of particles, but it's a non-trivial superposition. Okay, now let's check that indeed it works. Namely, if I apply gamma on this, I want to get 0. Okay, so let's do quickly the calculation. And what I'm doing, I'm plugging the expression for gamma. So this is what I want to check. I plug in the expression for gamma. And I apply it on this, and not to confuse with the indices, I denote the dummy index here by k prime. Okay, so it's uk prime plus vk prime. Vacuum, and now let's see. So what happens if we apply UK? We apply first the first term. What does it do? It gives me for first of all, we can reshuffle it up to the point where k prime equals k. Otherwise, it does nothing, right? Now, when ck acts on the first term has just a number times the vacuum.
0.
So you get 0, right? So the only non-vanishing contribution will be from the second term, because then it can annihilate this guy, right? And then you're going to get something non-zero, okay? So let me write what you get from the first term. Will give you, first of all, you'll get a product of all k of, okay, let's not, k prime plus vk prime. This is for all the k primes that are not equal to k, and then I get, and maybe there is some -1 to some power, but I don't care about it because it's the same for everything. So there is some minus to the power p, where I don't care what it is, because all I care is to see whether it's 0 at the end, right? So now, when I'm act with this on uk plus vk, then as we said, the first term will vanish. So the only contribution will come from this uk times vk times after I'm acting with ck on ck dagger c minus k, I will be left with a c minus k dagger acting on, okay, everything will act on the vacuum, okay, right? Okay. And now I apply the second term. What about the second term? The second term will annihilate, it will annihilate the second contribution, right? Because, why? Because it's c minus k dagger times c minus k dagger. It's the same quantum number twice. Okay, so I remind you, for fermions, this is 0. Okay, This is 0. So we will not get any contribution from Vk times Vk, right? But we will get contribution from applying this UK Ck on the second term again. So what will I get? Exactly the same thing, but with a minus sign. Okay, it's coming from this acting on, sorry, from this acting on this. Okay, it's Vk minus Vk times Uk times C dagger minus K. So it's exactly the same thing, but with a minus sign. Is that clear? All these we don't care about because they commute. Okay, they commute. We can reshuffle it. Actually, we don't even have a minus sign, I think, because it's only either 0 or a pair. So the number of permutations is always even. Okay, but these I isolate. And all I care is what it does to the one contribution in the product that is the same K. The same K. Okay? You have to repeat it. Maybe I'll just sketch what I showed you. Write it separately. Okay? So I have UK CK minus VK, don't have space, sorry. UK CK minus VK C minus K acting on UK plus VK CK C minus K. Okay, this is what I have. This is what I have. All the rest, all the K primes that are different from K are just a factor that that multiplies everything. Okay? And now I want to prove that this is 0. Okay, so how do I see it? I can easily see that this times this immediately gives 0. This times this immediately gives 0 because it has a double occupation. So I have only 2 contributions, one coming from this times this, right? And then it gives me UK times VK times C dagger of minus K, right? The second contribution is minus UK VK times C dagger minus K. So I get this times itself, which is 0. Okay? And that's true for any K. So we are done. So we found a ground state that acts like a vacuum for our new quasi-particles. Okay? And it is a state that has a non-well-defined number of particles, and therefore it's quite natural that the excitations will also be with superpositions of number of particles. In fact, what this operator does, why is it an excitation? Because we can think of it as something that breaks a pair. It breaks a pair. Okay? And the pairs are these states. You can think of them as kind of bound pairs, although if you look at them, they're not really strongly bound in our model, but they're in K space, okay? They're defined in K space, so it's not like we have a bound molecule. But it is a pair that has some correlation between 2 electrons, and what is their center of mass momentum. It's zero, okay? It's a zero center of mass momentum, and it has opposite spin, so it's a singlet, okay? Spin singlet. Okay, so we now start to understand what is the nature of the ground state, and it's very beautiful, and in fact, it also has other nice properties that I mentioned last time, which is that this delta is only defined up to an arbitrary phase. It's a complex number that is defined up to an arbitrary phase. Let me discuss it a little bit later. But I don't have time to show you why this state is superconducting. That's actually much more difficult to show, but it's not the subject of the course. Okay? So I'm actually supposed to give you a prescription how to use techniques, and then in your later studies you'll understand how it is connected to the phenomena of superconductivity. So I'm owing you only one thing, but this thing is crucial. Why is all this true? Because I assumed that this expectation value is non-zero. Otherwise, I'm back to the free electron gas, right? So I have to prove to you that this expectation value is indeed non-zero, and namely that this equation is consistent. For non-zero, it has to have a non-trivial solution, because delta equals 0 is always a solution. Okay? All right, so let's do it. We assumed it. That's the whole point. There is a delta. Everywhere there is a delta. If the delta is 0, everything is back to trivial. Okay? It has to be non-zero. And there is one thing that, okay, so yeah, we will get to it. Okay, so let's take this equation, and now what I want to do is to write down this expectation value explicitly, knowing that now that I already know what is this ground state, how does it look, and I know that it's a vacuum for the gamma k and gamma k dagger. So I have the tools to calculate it in terms of the new quasi-particles that I described. Namely, I know that for the gammas, the ground state behaves like a standard vacuum in the sense that we have, let's write it here, that gamma k prime, gamma k dagger, gamma dagger k prime, and gamma k dagger, gamma k prime. This is 0 for any k and k prime, and gamma k prime dagger, this is non-zero, and it equals to delta k prime. Okay? How do I know it? Because again, the BCS state is a ground state. It's like a vacuum for the gammas, and for the vacuum expectation values of these operators are just a standard thing that you get for fermionic operators. Okay? So I know this. But my expectation value is now written in terms of the C's and not the gammas. So I have to use the transformation, in fact the inverse transformation, to express them in terms of these things, and then I can calculate.
In this case, the state is BCF.
Yes, yes,
And
yes.
in this case, the state is vacuum.
Every time I write this, this is how I define it. Okay?
Yes.
Okay?
If this vacuum, it's 0.
Yes.
Okay.
Right. Right. Okay? So, okay. So let's write it in terms of the gammas, and for that I need the inverse transformation. So let me write it here. CK is UK gamma K plus VK gamma dagger minus K. Okay, this is the inverse of the transformation I wrote before. Okay, because it's the inverse, here I have a plus and not a minus. Okay, and therefore, let me write it here. Okay. So, C minus K CK is, I'm just plugging it in. The first term will give me UK times, times gamma of minus K minus VK gamma K dagger. Now, why did I get it? Why do I have here UK and minus VK? Because actually, I should take this, but plug in minus K.
But UK is...
But UK is symmetric, and VK is anti-symmetric. And that's why the first term is with the same sign, but here I have a minus. Okay? And the second one is just exactly what I wrote. So it's this plus VK gamma dagger of minus K. And I have to now take the expectation value of the whole thing, and it has 4 terms, right? If I open the brackets, I have gamma gamma, gamma dagger. What are these going to give? 0. Actually, and then I have, so we must only get contribution from something that has a product of UK and VK, right? So UK, so one candidate is UK gamma minus K times VK gamma dagger minus K.
It's only that.
And that is actually non-zero. In fact, what is it? It's exactly going to be UK VK times the expectation value of gamma dagger with the same index, which is 1. So it's just UK times VK. Okay? What about the other? We still have another term to take care, but that's also 0 because it has a gamma dagger gamma. Okay? And therefore that's it. So I can now plug in the result. I go back to my expression for delta, and I plug it into here. And I get V times sum over K, and UK times VK. Okay? And now this has it looks like I can always write it down. However, the question is, what is UK times VK? You can easily see that if one of them is 0, I get 0. So in order to get something non-vanishing, what do I have to have? I have to have a non-trivial product of UK and VK. Okay, UK and VK complement each other to 1. If we look at the square of them, they're like cosine and sine. So they cannot be 1 and 0. And therefore, actually, this combination, this product, is called a coherence factor. Okay, so it has to be non-zero. What is it going to be more precisely? So I'm just giving you a result that you will derive next week in the tutorial, but UK times VK can be very simply expressed in terms of delta. So if you solve for the transformation for the U and V that diagonalize the Hamiltonian, you find some expressions for U and V. I don't write these expressions. What I'm interested in is just the product, okay? And notice that if UK is like a cosine theta and this is a sine theta, then the product is 1/2 of a sine of 2 theta, right? This is just a trigonometric expression. And you can prove that this thing is nothing but delta over EK. So the whole thing, this coherence factor, is given by a very simple expression, okay? Again, you'll see why next week. It's just algebra, nothing more. And I remind you what is EK. It's the energy of the quasi-particles, which is, okay? All right, so let's plug it into the equation. I'm getting that delta must equal V times the sum over K of delta over 2 EK.
EK always depends on delta.
EK always depends on delta. But notice that here in this expression, delta is a constant. It's independent of K.
Okay.
Right? I can actually, so you are right, EK of course depends on delta, but it has some value even if delta is 0. But the problem is, not the problem, the beauty is that delta also appears in the numerator. And because in my model it's just a constant, it's not K dependent, I can move it outside of the sum. And let me write it like this, also the factor of half here. So I get a V times delta over 2 times the sum over K of 1 over EK. Okay? And this is called,
We can't cancel delta.
Very good. Now we're getting there. So first of all, this is called a gap equation. It's an equation. It's a self-consistent equation that tells us what is delta in terms of some function that depends on itself, right? Now, you're saying we can cancel delta, but okay, but by canceling delta, we are assuming that there is some solution that is non-zero. Okay? I mean, delta can always be 0, and then the equation is trivially satisfied. You agree?
Mm-hmm.
But now let's assume that it's not vanishing. And then you are exactly right. We can cancel it. Okay? So cancel, and then what we get is, let me write the resulting equation. It's on the left-hand side, you'll get just 1. And here you get V over 2 times sum over K of 1 over the energy. And let me write it explicitly. It's the square root of psi K square plus delta square. So this expression is whatever it is, you solve the sum, you get a function of delta, right? And this function has to be such that if you multiply it by V over 2, will give you 1. Okay? It's not guaranteed that you'll get the solution. Actually, let me ask you this question. What happens if V is negative?
It can be...
There's no solution. Okay, and I'm reminding you that V positive is defined in such a way that the interaction is attractive. So first of all, now you see why we needed attractive interaction. If there is a repulsive interaction, this is never a solution. Okay? If it's attractive, there is a solution. Okay? And in fact, we can solve it very easily. Okay? So, and in fact, okay, now it's actually a technical thing. To solve this sum, you have to know the dispersion, and you can, for metals, for example, you can make a very simple approximation. Let me write it just quickly somewhere. So we basically have to solve the following equation. Sum over K, 1 over square root of psi K square plus delta square has to be equal to 2 over V, right? Something like that. Now, we can approximate for metals, we can approximate the sum over K can be replaced by an integral over psi of some density of states, right? This is always true, by the way. You can always go to replace the sum over K by an integral over energies, because the variable here is psi, right? It's some function of psi, and G of psi, the density of states for metals, can be, for a very good approximation, set to a constant. Okay? So we will approximate it by G of 0. Okay? The density of states at the Fermi level, which is Fermi level is psi equals 0. Okay? Yep.
So in the gap equation, if delta is k dependent, then why did you take it out?
No, it's not k dependent. So sorry, I erased it. Delta is not k dependent. Delta is, let me rewrite it. Delta is defined as sum over k of something. So it doesn't have an index k. Okay? You are right that I can assume, so here I assumed a very simple case where the pair is a ck and c minus k. I could assume that the pairing is between states with finite center of mass momentum, for example. In that case, delta would have a K index. So you can think of pairings that are less conventional, okay? But the simplest version is that delta is independent of K, okay? Okay, and it's by the way, it's any complex number where the gap equation only sets constraints on the absolute value, which is the energy gap, okay? And so anyway, if you replace this by an integral, so you get something like integral over psi of 1 over square root psi square plus delta square has to equal 2 over v times density of states, something like that. This integral gives a logarithmic divergence, not divergence because it's cut off by delta. Actually, psi also has an upper cutoff because the energy can be only as large as the band gap or something like that. So there is always actually some cutoff energy, okay? What is this cutoff? Now it comes to details that I don't care about, but the result is there is a solution to this, and what it gives you is that delta equals some energy scale that is of order the cutoff, but it's multiplied by an exponential, actually this factor of 2 must go away. So it's something like that. It's exponentially small. All right, and yeah, that's it. It's a solution, but it's a solution for, again, it's a special case that the normal state is a metallic. It has a metallic spectrum, and that the pairing is the singlet pairing of K minus K that I described before. All of that, but that's like the model that BCS proposed as an explanation for superconductivity in metals, right? Superconductivity was first discovered in metals. Only in the last decade we see that it exists in a better version of it in all sorts of complex oxides and other stuff, okay? So this, by the way, is a very good prediction of the theory that, of course, they got the Nobel Prize for a good reason. They had many predictions that were experimentally verified. Okay. So I think here we should stop. And everything else you want to know about this, you'll see. I'll write some summary to post on the course website, just for your information, not for the exam. And if you are interested more, you can take a course in superconductivity. Ruchman is giving such course every now and then, and he's a good teacher. Okay, so okay, so we are done with this. In the tutorial of next week, Sar is going to fill up some gaps and show you the details of how you get this result, for example. But this is just technical. Okay, any questions before I move to a new subject?
לא מניח שלמדה פסאי שווה בערך ל-G0.
I said that for metals it's a good approximation. Okay, because in the metals the density of states usually is it has some power dependence on the K, but if you're expanding near the Fermi energy, it's basically a constant. Okay? You can replace it by a constant.
וגם אני יכול להניח שזה נמצא באזור מאוד מאוד ספציפי פה הדבר הזה שלא חשוב.
What do you mean?
כי את הגדרת את זה בין EC למינוס EC כל
No, right, but the whole phenomena, actually, by the way, because delta, you see, delta is very small because it depends exponentially on the interaction. And the interaction, in reality, this V is small. It's a small, so you basically get e to the minus some very large number. Okay? So the order of magnitude of delta in metals, if you translate it to temperature, will give you of order 1 Kelvin, as opposed to the Fermi energy, which is how much in Kelvin? Who remembers offhand? It's 10,000. Okay, so delta is so much smaller than the Fermi energy that the whole phenomena is existing very close to the Fermi level. Okay, there's almost no dispersion in K around it. Okay, if you look at what happens to the spectrum, so if you had, originally you had this parabola of a free electron gas, and this is the Fermi level, then in the presence of superconductivity, the spectrum now will develop some very small gap, but this is delta or 2 delta, something like, it's very close to the Fermi energy. Okay? So this approximation is good. For metals, I emphasize. A lot of things change if you want to develop a theory for superconductivity in cuprate compounds or in, I don't know, twisted bilayer graphene. You can throw all this to the garbage. It doesn't work, but what is important is, forgetting about the details, is that attractive interaction, unless you have something else that comes in, some other kind of special order, will always turn a material that is a free electron gas to a superconducting state, okay, to a superfluid, in fact. So the Fermi sphere is unstable to attractive interactions. Okay? If the interaction is very weak, maybe that the critical temperature will be millikelvin. Okay? It can be very small, but it will be there. If you go to 0 temperature, this will be the ground state. Okay? Whereas repulsive interaction is, although it may be strong, it's less destructive. This is an amazing fact. Okay? Less destructive in the sense that it doesn't change the nature of the state. It only normalizes the energies. Okay? Unless it's that strong compared to kinetic energy that it also gives you some other ground state, but that's okay. In any case, what in terms of the idea of mean field, this exercise also shows you how to use the idea. So the idea is you make a guess, maybe a wild guess, maybe it's wrong guess, but you can test it and derive some self-consistent equation, and if it has a solution, maybe you're correct, but maybe not, because maybe there's a competing ground state that has lower energy. And then you completely missed it. So you never know. It's a wild guess, but this is one of the games that people play when they try to develop a theory for phenomena in complex materials. Okay? All right. So let's move to the next topic. And the last topic of the course. We don't have a lot of time left. So, okay, so the last topic we are going to introduce a new formalism for quantum mechanics that was proposed by Feynman. And we're going to first start with a single particle problem. So this is the kind of problem that in undergraduate studies you already learned how to solve using a Schrödinger equation and all that, but Feynman suggests a different approach that has one advantage of it is that it's, or one of the advantages is that it's very intuitive. It gives you a good prescription how to go to the classical limit, because we know that quantum systems in some limit where you can assume h bar to be small compared to other quantities with the same units, then you should go back to classical mechanics. And the Feynman's formalism, which is called the path integral, is exactly that. It's an approach that allows you to formulate quantum mechanics in a way that it will be very easy to see how you approach the classical limit. Another thing that for which it's very useful is in many body systems like the ones that we just described in the past few weeks, which are problems with many particles with interactions, the path integral formulation gives you a way to approach them that you can relatively easily go even beyond a mean field approximation. Okay? So the mean field approximation that I showed you has some weakness. It's, first of all, it's usually equivalent to some kind of leading order in perturbation theory. So it works if you have weak interactions, and it gives you maybe some minimum energy solution, but you have to prove also that it's stable, and then you have to check the fluctuations. And the path integral formulation allows you to do it in a systematic way. Okay? So, so what is the idea? And today we're first going to start with a single particle. Okay? Single particle, you have a Hamiltonian that has kinetic energy and potential energy. And there are operators that do not commute, okay? Because the kinetic energy, let me write it explicitly, is p squared over 2m, and v is some v of q. Okay, so what? Of q. Let me. In this lecture, I'm going to denote them by p and q, coordinate and momentum. Okay, it can be some generalized coordinate, by the way. But there are q and p are quantum operators that obey the canonical I h bar. Okay?
אז אופרטור הפוטנציאל הוא אופרטור של אופרטור אחר?
Yes.
Okay.
Yeah, it's a function of Q, of the operator Q. Okay? So V and T do not commute. Okay, and now I want to ask the following question. Suppose I prepare a particle at a well-defined position in space. Okay? So at time equals 0, I have a state that I will call, psi of 0. This is the wave function at 0 is the state Qi, okay? Qi, I is for initial. Now, after some time, so I prepare a wave packet. What is the state Qi? It's the state that if I look at how it looks in Q space, it's a delta function, right? It's localized only at Q equals Qi, okay? But now I allow the wave function to develop in time, and in time it will be influenced by this Hamiltonian, which has kinetic and potential energy, and it will develop according to this Hamiltonian in time. And after some time I'm going to get a final state that is no longer a delta function in Q. So if I want to write it quite generally, T, capital T, don't confuse it with T operator, okay? But just that this T is the final time. This wave function is given by e to the minus I h t of psi of 0, and throughout all the next lectures, from today to the end of the course, h bar will be 1. Okay, let's agree on that?
Yeah.
Good. Okay. Because then otherwise I always have to write this denominator, I don't like it.
ואת אומרת שסיגמה F זה 1 בעצם?
מה?
אז מי בדיוק 1 עוד פעם?
h bar.
H bar, אוקיי.
Okay? We choose units where h bar equals 1. Okay? So frequency and energy are the same. Okay? Great. So, okay, so this is it. So there is a state that evolves. I hope this you have seen, right? This is a solution of the time-dependent Schrödinger equation. And then we can ask the following question. This wave function, whatever it is, and is going to have some overlap with a state that is localized in some other coordinate QF final, and we can ask the question: what is the probability for this to be found, for the particle to be found in position QF? Okay, so let me first draw a diagram of the problem that we're asking. So I'm plotting here a diagram where the horizontal axis is space, okay, and this is the t equals 0. This is my q axis, and this is qi, which is some position, some coordinate, and my initial wave function is a delta function localized on qi. Now, as a course of time, this is the time arrow, goes down in my picture. It progresses in time. Something happens to this wave packet. Okay, I don't know what, because it depends on the Hamiltonian, but it will evolve. Let me plot. So after some time, it will now maybe look like this. After a later time, it will look like this. Okay, and then after time, now let's stop our experiment at time equal capital T, which is my final time, and here I'm plotting the q-axis again. And in my final time, the state will now be, I hope I can use the red color, it will be something like this. This is the way, this is how the particle evolves, okay? Now the question is, I'm asking is, I want to perform, I have some detectors spread over all my Q axis, and I want to measure what is the probability to find a particle here, okay? And this I call QF, okay? Now, what is the probability to be F? It's actually the absolute value square of the overlap between psi t and QF, okay? In other words, okay, so, and in fact, let me rewrite this as QI, right? So, the quantity that I want to compute is called a propagator. And, sorry, it's a function of, three variables, Qi, QF, and T, exactly. And it is defined, if you like, as the overlap of this state with QF. Okay? And this is the amplitude. If I want to know probability, I have to put an absolute value square. And then I have a physical quantity that I can measure. Okay, so in principle, this is a measurable quantity. And of course, I can solve it using solutions of Schrödinger equation, finding eigenstates of the Hamiltonian, and all sorts of that. But that's not my purpose. My purpose is to represent the problem in its most general definition, without telling you what is V, in a different formalism. And the advantage, the mathematical advantage of the new formalism will be that we are not going to need to deal with operators that do not commute. We will get rid somehow, not get rid, hide the commutators under something that will give us, eventually the problem that we have to solve will boil down to solving integrals of numbers, not of operators, okay? So, because this is usually when you have something like this, what is the meaning of e to the minus iht? It's an exponent of an operator. So if you want to really do a calculation with it, you have to expand it to an infinite sum, which involves the application of the Hamiltonian many times at different times. It's a complicated calculation, okay? So we are going to formulate it in a way that will be easier to solve, at least for some cases, okay? All right, so what is the idea that we're going to use? The main complete, yeah? Yeah, sure. That's what I want. I'm giving you a problem that I want to solve. Okay, why? Because I want, because I can. And I'm going to show you a technique of how to calculate it. Okay? This is just a definition of a quantity that is called a propagator. Okay? In some books, by the way, it is denoted by K, capital K, but I don't know. It's, I like it better because it's also called in some cases a Green's function. Okay, so good. So the idea, so first of all, I want to emphasize what is the technical difficulty. The technical difficulty is that in the exponent, we have a sum of non-commuting operators, but I'm going to show you that if we divide our timeline to very, very small bits, okay, imagine that you track the particle, you track the time evolution of the particle over time from 0 to capital T, but with infinitesimal time steps, okay? In each infinitesimal time step, we can make an approximation that will allow us to treat the kinetic and potential energy as commuting object, okay? Why is that? Okay, so first of all, you agree that, let me start as follows. So let's divide our time capital T to n pieces, okay? I'm looking at my timeline from 0 to T, and I divide it to infinitesimal time slices. Each time slice is dt, okay? We call it dt. And capital T has capital N such time slices, such that dt is T over N, okay? Now what is N? It's in our calculation it's arbitrary. Let's take it to be something, but it's much bigger than 1. And in the end, we're going to let it approach infinity. Okay, so in fact, what we really like to do is to do these small time steps and then shrink them until you get the real problem, which is a continuous time evolution, okay? So, n in the end of the calculation will send to infinity, okay? And that's the idea. Now, so therefore, I can write, when I write the operator e to the minus I h bar h times t, I can look at it as a product of the operators at each time unit. So it's going to be e to the minus I h dt times e to the minus I h dt, where here I'm basically dividing the time to this, and I have n such terms in the product, okay? And each of these exponents describes the evolution only in this small time step, okay? So these are n terms. It's a product of n terms. Now, why am I? Notice that actually t is a sum over dt's from 0 to n, but I write it as a product. Why am I allowed to do this? It's not obvious because if I have what?
Called the commutation relation.
Right, exactly. So let me now write a very useful formula where shall I write it? Let me write it here because we're going to use it. So this is called the Hausdorff-Baker, and I hope I'm spelling it right, but I'm not sure. So please Google it. Maybe there's a double F. And this is what it says. If I have an exponent of a sum of two operators, A and B are sum operators that are generally non-commuting. The exponent is given by e to the A times e to the B times, there is a correction. Let me just remind myself if it's plus or minus. Yeah, so it's actually minus. One half A, B, plus, or actually here there are some additional corrections. So in most general case, there is an infinite expansion here which comes from higher order commutators. Okay? In our case, we will not need it anyway, but this is the general formula. Okay? It's called the Hausdorff-Baker. And in many practical cases, we can stop here, because, for example, if the commutator is a constant, then it stops the series, but otherwise it's more complicated. Okay? So this is, of course, for numbers, this is an identity, right? Without the correction. But because we have to make a commutator here, this is what you get, and you can easily prove it by using the definition of the exponential as an infinite sum. Okay? All right. So let's keep it as in mind, this formula. And now, but notice that here I am allowed to replace the sum by a product because it's the same operator. It's just H. Okay, H commutes with itself. Okay.
But we have T plus V.
No, that's right. But the H, the total H, commutes with itself. Okay? But within each such exponent, I have T plus V. And that's where I have to vary. So let's take just one of them and see how we can use the fact that this dt is small. So if I'm writing explicitly what is e to the minus ih, dt, e to the minus ih dt is e to the minus I t plus v dt, and I very much would like to replace it by a product of e to the minus it dt and e to the minus iv. But let me be careful and use the Hausdorff-Baker formula. So it's given by this times e to the minus I potential energy times, and here I have the commutator. But the commutator, let's just look at the first term, because there's actually an infinite expansion, as I said. But the first term will be minus I squared times T V times dt squared, right? Right? And if I look at the commutator of a commutator, it will go like dt cubed and dt to the fourth. So overall, what I have here in the exponent coming from here is of order dt squared. Okay, and dt goes to 0.
You can explain why is dt square?
Yes, because what is a commutator? It's the commutator of this times this. The whole thing in the exponent. The whole thing. Yes.
Okay.
Yes, of course. Right? So that's exactly the thing, that the commutator, because it's actually a product, a combination of products, it's quadratic in the time step. And the third order commutator is cubic and so on. Okay?
Mm-hmm.
So basically, in the limit that this factor goes to just 1 in the limit that dt goes to 0, which is the limit that we are going to focus on. Okay? And that's great, because then what I can do is to replace the operator e to the minus iht. I can replace it by a very, very long string, but of terms, but each term in the string is simple. It's a product, it's an exponential of operator that is either a function of p or a function of q. Okay? So let me just write it down, and then we'll take a break. Yes, just write this. So we're going to basically replace it. This is an approximation by e to the minus I t dt, e to the minus I v dt times, once again, the same thing, and blah, 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 and this I'm going to repeat n times, okay? Okay, so let's take a break and see how we progress with this. Okay, so let's start again. So this is where we are at. We are going to show here a way of calculating this propagator, where the idea is that we divide the timeline to very, very tiny steps, and at the end we're going to take the limit that the time step is infinitesimally small and goes to 0. So now what I did here, what I have to calculate is to take this operator and sandwich it between some qi and some qf, okay? And the first thing I do is to rewrite it as a product of many such terms. Each of them is either commuting with q or with p, okay? The momentum and coordinate, yeah?
Can you explain about n equal to 1, n equal to...
No, this is just, so I divide it to n terms, capital N terms. The index little n is going to be an index that we keep track of, and it goes from n equal 1 to n equal capital N. Yes. It's the n is the index of, it's going to be a parameterization of the time in terms of the time step.
And starts from 1, not 0?
From 1.
Okay.
Why? Because just this is not important, but I want to define qi as the coordinate at zero time, okay? All right, so, okay, so the idea, the next thing I am going to do is to use the fact that I can always use, in between each such terms, it's a product, right? And in between I can always put 1, right? But 1 I can write as a resolution of identity. What is the resolution of identity? I can always write it as a sum over some complete set of eigenstates, alpha, alpha. Right? This is the usual quantum mechanics. Alpha must be in a complete orthonormal set. In particular, such a quantum number alpha can be either coordinate q or momentum p, right? So I can write it as dq dp, and then p q q, right? Actually here I have a product of 2 resolutions of identity. I sum over all momenta and all coordinates. And for each of them I have this projector PP, QQ. Okay? And I can also equally well write it like this if I want. I can change the order of Q and P, doesn't matter. And I can write it like this. This is also an identity. Okay? Now, what is the trick? The trick is that I'm going to place this identity, this resolution of identity, many, many times in between these time steps. Okay? So in particular, here, here I can plug it into here. Now I do want to distinguish the 2 cases just for good measure. And here I want to put this resolution of identity, but because it's time step n equal 1, let me write it as dq1 dp1 p1 p1 q1 q1, okay? And so this is at n equal 1. Then I want to put another resolution of identity at, okay, let me write maybe the general expression that I'm using is going to be that, so you see I can plug in this with Q1 and P1. Then at n equal 2, I do the same with Q2 and P2. Then this, I do it many, many, many times until I get to n equals capital N, okay? So I'm now writing the nth step, somewhere in the middle of this long chain. I have an nth stage, and I only focus on one because then, of course, it repeats itself with changing index where little n goes from 1 to n. Okay, good. So let's do it here.
רגע.
It's alignment. אוקיי?
למה אנחנו רוצים גם את התנא וגם את המקום?
כן, אוקיי.
תכף תראה. אוקיי?
האינטגרל הוא על כל המרחב ועל כל התנא?
So each time, what I'm doing here, this is an operator, right? But I'm always allowed to plug in between every term in the product. I can introduce a resolution of algorithm. Yeah?
זה לא קשור לשיעור.
זה לא קשור.
אוקיי.
Okay, so you know what? Let me just erase everything and write the nth step. Okay, the nth step in the string. Where n is between okay, 1 and n. Okay, so I have dot, and then integral dq n plus 1 dp n plus 1 of no, sorry. This will be more convenient to write it like this. We'll see why. Okay, and here I have yeah. No, sorry. Jumping ahead. Okay, now I have Qn. Sorry. Okay. So this already belongs to the next string. I have something like that with Qn and P and wait. Confused about something. Sorry.
We have also ket Qn plus 1.
Yeah, so yeah, so of course I have, so here I have, so okay, so let me just let me put here the dots, because of course this is not the whole thing. Now I have how do you call it, a bra or ket? I have the ket of Q plus 1 and the bra of Qn, but they already belong to the next thing in the chain with n smaller by 1. So I want to keep only this, where I have this part and this part. Okay? Okay? This is part of a resolution of identity, and of course here I have Qn plus 1, which I plug in and I integrate over it, and so this is part of the next resolution of identity.
רגע, את יודעת רגע, אנחנו עושים את זה באמצע. רגע, אבל אם אנחנו עושים את זה באמצע, אז למה יש פה רק שניים שנמצאים פה בין שני ה-T וה-V, ויש שניים אחרים שיצאו החוצה? יש איזושהי חילוק?
No, so actually what I have here, to be more complete, let me be a little more careful. I mean, the integrals I can always pull to the beginning. So I have integral over Qn and Pn plus 1 and so on. But here I also have a Qn plus 1. Okay? And then I will once again can put IV and T. Okay? And then it will look very much like this with n plus 1.
רגע, אבל אנחנו אמרנו שיש לנו כאילו את שני האקספוננטים האלו שהיו במקור, נכון? ואתה אומר שבין שניהם את רוצה
So if you like, I here between this and this, I plugged in, let me do it more clearly. I plugged in the resolution of identity. Okay? Okay? But now I also have another resolution of identity, which is integral Qn, and but here I don't write it explicitly, but it's there.
אז כאילו Qn זה שייך לזה הקודם, וה-Qn ועוד אחד זה שייך...
Exactly, right. So in fact I do have here a Qn of e to the minus it dt, and the rest I'm not writing. Okay? So here, if you like, this is already a full thing. This is a resolution of identity, Qn, integral over Qn.
אוקיי, אז למה Pn ו-Qn לא צמודים אחד לשני כמו שהם היו אמורים להיות?
Because there are numbers, so the resolution of identity, the integral I can always write here, right?
אוקיי, כן. כן.
Right? It's just a summation.
אני רואה כאילו ש-Pn ועוד אחד, Pn ועוד אחד, שהם התחלפו עם ה-EV או משהו בסגנון שזה...
No, but wait. So you agree that I can put the integral here, or move it here, or move it to the left, and it doesn't matter, okay? So for convenience, I leave it here, okay? Now there is Qn plus 1, integral over Qn plus 1, which I'm not even writing. It's over there on the left, okay? And it's put between two operators, okay?
Okay.
So if you write it carefully for yourself, you'll see that it's always, I just put an identity resolution, but each time I'm writing it a little differently, because here I want to integrate everything that depends on Pn plus 1. Okay? Okay. So I actually want, so this is an infinite, this is a long chain, but I want to focus on the part that is, let me use another color for it. I want to focus on this thing, which is a well-defined number. Okay? And the same structure will repeat itself. Okay? Good? Okay. Now let's see what we have here. So, and why did I use this order of the Q's and the P's states? Because let's first focus on the expression. Here I have a matrix element of an operator that depends only on the coordinate Q, right? So, and it acts on the state Qn, right? So, therefore, this state is an eigenstate of this operator, and therefore I can replace it by a number. And what will be this number? It will be e to the minus I v of Qn times dt, right? So let's do it. So, with your permission, let me erase the blue color. Sorry for the shrieks. Okay. Great. So let's deal with this. Let's first deal with this. What is this? As I said, it's I'm allowed to replace e to the minus I v operator dt by a number. But if it's a number, an eigenvalue, I can take it out of the overlap, right? So what you have here is Pn plus 1 inner product with Qn e to the minus I v of Qn dt. You agree? Okay, I use this eigenvalue equation, got a number, took it out of the matrix element, and what I get now in the exponent is a number. Okay, it's a function of, it's a value of the potential at coordinate Qn. I also know what is this. What is this overlap? Exactly, this is the projection of the wave function with momentum Pn plus 1 on coordinate Q, and we know how to write it, right? It is actually given up to a normalization factor by e to the minus I, because it's the P is here and the Q is here, it's minus I P n plus 1 Qn, right? Okay, let me see if I got it right. Yeah. Great. So the whole, so this matrix element, I know exactly how to write it. Okay, it's this exponent times this exponent, both of them are numbers. Now I do the same for this guy. And once again, I get an eigenvalue because now the e to the minus it acts on a state with well-defined momentum, right? So it can be replaced by its value at Pn plus 1. So this is given by an exponential factor of e to the minus I t of Pn plus 1 dt times the projection between Pn plus 1 and Qn. And this projection is the same normalization factor times e to the I Pn plus 1 Qn plus 1. Okay, agree?
מה זה n? זה נורמליזציה.
Yeah, it's a normalization factor, which actually we know what it is. Let me write it down. It's 1 over sorry, it's 1 over 2 pi. Yes, it's 1 over 2 pi. Okay?
Square root.
Or square root.
It's
Square root. Yeah.
convention.
Square root. Yeah. Right. It's 1 over square root 2 pi. Okay? Okay?
איך ידענו שזו הרצאה עוד פעם שמינוס i pn ועוד 1 qn זו הרצאה מגיצור?
בכל מקום, הרחבתי עליו.
Yeah, so I remind you that this is 1 over square root 2 pi e to the I pq, right? And if the p is on the left, it's the complex conjugate, and therefore it's with the minus.
Okay.
Okay? So this is with minus I, and this is with plus I. And that's actually important. Okay? All good? Now let's collect. So what did we get here? Inside the integral of Pn plus 1. And all the integrals, actually, I can shift all the way to the left, because in the end, I'm going to get a product of many, many, many numbers. And in the last step, I will have to integrate over all these variables, Qn and Pn. Okay? Great. So inside the integral, I have a product of 4 things, and I'm now writing them exactly. Yes, I will actually write it here. So what I'm now doing is, let me put in the frame only the numbers without the integrals. Okay? And this expression equals there's a factor of 1 over 2 pi because I have n square. And then I have the following thing. First, let's take care of these exponents. So I have here e to the I Pn plus 1 times Qn plus 1, but minus Qn, right? So let me write it as 1 exponent of e to the I Pn plus 1. Oh, this is not working. Qn plus 1 minus Qn, right? And then I'm left with e to the minus it at Pn plus 1 dt times e to the minus iv, but these are now numbers, okay, no longer operators. So I can just sum them up. So I'm getting e to the minus I t of Pn plus 1 plus v of Qn times dt. Okay? Now, actually here, because I chose notations such that this Q is a different time step, but to a good approximation, since the time step is going to shrink to 0, this is nothing but the Hamiltonian, the total energy or the total Hamilton, the classical Hamiltonian at time step little n, okay? And now here we have something interesting. In the brackets I have Qn plus 1 minus Qn. This is the difference between Q at consecutive time steps. Okay, so I have an interval of time. If this is n, this is n plus 1. Okay, the difference in time is dt. So I'm always allowed to multiply and divide by dt. Okay? You agree? Just this expression in the exponent. Why do I want to do it? First of all, you'll see that in the end I will get something times dt. Okay? But what is this? What is Qn plus 1 minus? Exactly, in the limit that dt goes to 0, I can replace it by a derivative. Okay? So I can actually replace it, this whole thing, I can replace it by q dot, the time derivative, at time step n. Okay? And it's that times p, and then again, because of what I said, if dt goes to 0, then this Pn plus 1 can be replaced by Pn to a good approximation. Okay? So what did I get from all of this? Let me simplify it by one expression. This all factor is actually 1 over 2 pi times an integral of I Pn q dot n plus, minus h of Pn Qn, where I made the approximation that Pn plus 1 and Pn are the same. Okay, maybe it was, I should have labeled them a little differently. Okay, define my string differently, but it's all the, and very important, times dt. So the I and the dt are common factors. Okay? Great. What did I get here? And notice that this Pn and Qn are just the coordinate and momentum of some trajectory at time, and some intermediate time, which is little n times dt, right? So in fact, I can just replace it by in the limit that dt goes to 0 and I'm going to a continuum, I can just replace the index n by the time t at intermediate time between 0 and capital T. Okay? And all of this is just an infinitesimal time step, but I will have the same for all times between 0 and capital T. And when I sum them up all together, what do I get? An integral over time, right? So now this is exactly what I do. I go to the continuum limit. Now I guess I can erase all of that. And then notice that everything here at the end has to be sandwiched between Qi and the Qf, right? Because I want to calculate the propagator. So let me tell you what you get if you do it carefully.
הסכמה היא בעצם במעריך, נכון?
Yes, exactly. Exactly. What I get in the end, because all of these are numbers, in the end what I just get is an exponent of an integral, and inside the integral, this is the function that you have. So this is what I do. I turn the Pn and Qn, I replace by P of t and Q of t, where t is just n times dt. And I get the following expression for the propagator. I get an integral of many, many variables. It's a product of n going from, sorry, let me write it like this. So it's the limit when n goes to infinity of an integral over n product of n going from 1 to capital N of d q dp over 2 pi. This is the normalization factor. And here I have what am I integrating over? The whole thing is an exponent of integral from 0 to capital T dt of p q dot minus h of p and q. Okay, and there is an integration here where I have constraints on the, actually, you know, let me, for simplicity, no, that's fine. So here I'm putting some boundary conditions because at the end I sandwich it between Qi and Qf. Qi is the coordinate at time 0. Qf is the coordinate at time capital T. So I'm constraining the integration such that, and also the integration over the variables p and q here, so that q of 0 is Qi, and Q of T is QF. Okay? All right, that's what I get. And let me erase the rest so that it will not confuse. Now I can erase this stuff, right? Okay. Now I want to write it a little more pleasantly, but first, let me ask you, what is this? Exactly, right. Okay, this is a Legendre transform of the Hamiltonian, which gives you a Lagrangian. So this is actually Lagrangian written in terms of let me write it in terms of P of T, and it's a functional of P and Q at this stage, right? And the integral of the Lagrangian over time is?
The pull action.
Action, right? So what you have in the exponent is the action. Actually, if I bring back the h bar, because h bar here was 1 for convenience, but actually the units of h bar are units of action, right? So if I bring back the units, what I get in the exponent will be e to the I s over h bar, where the action is an integral from time 0 to t of the Lagrangian. Okay? So let me write the final result a little more conveniently. Can I erase this? Okay. Just write a compact expression.
רגע, אפשר לעשות אבל איך תצפית לצורך העניין על שני מצבים? לא, זה לא תצפית, זה פשוט מה שעשינו פה עם המכפלה הזו, מה שעשינו במילה זו כאן. אז אנחנו רוצים לרוץ על הזמן מבחינתנו? כאילו, איך האינטגרל הגדול, כאילו...
No, what we got in the end was a product of all the time steps, but then we replaced the product by an exponent of the sum. But the sum is an integral. Okay? Okay, I got in the end, what I got is an exponent of a sum over n, little n, of something that depends on qn times dt. But the qn and pn I can replace by q of t, just like anytime we go to the continuum limit, and that's like gives me an integral. So the final result is this: qi, qf. This is the propagator equals something that I can compactly write as capital D of P. This is a notation for a differential that is a product of infinitely many intermediate differentials of e to the I s, where s, and it's calculated under, this integral is calculated under the constraints or boundary conditions that you start from qi and you end at qf, and in the middle your action is an integral from 0 to capital T of Lagrangian. Okay, and the Lagrangian is PQ dot minus H. Right? Okay, now what is this differential? And this is just a definition. Let me write it on the side. D of P and Q is the limit where n goes to infinity of the product n going from 1 to n of dpn dqn over 2 pi. So it's a many-dimensional integral. In fact, it is an infinite-dimensional integral. When we go to the limit of capital N going to infinity, the differentials are, the indices, there are infinite terms in this product, but it shouldn't bother us because formally we can always do the calculation at finite N and then take the limit, okay? Now, this expression is actually very, in fact, okay, I'm not done with it. Let me do one more step before I get the final expression that we want to keep for calculations, and then I will talk about the physics, what it means. And it's very interesting that the action comes in here. Okay? Because you're already going to see so there are two things I want to say about this expression. First of all, it's just a regular integral. I got rid of the operators, of the commutators. All of that is hidden somewhere. It's hidden actually in the form of the free wave functions that we use, but eventually it's a regular integral. It's integral of many variables, but you know how to do it. You do it all the time in statistical physics, right? There's no problem, especially when the integrals are Gaussian, because then we have an exact formula. Otherwise, we have to make an approximation. But there's another thing. What is the function we are integrating over? It's an exponential of I times the action. And this action is dependent on a trajectory. Okay? So there is a trajectory. For any time t, you can have some coordinates, some momentum. There's a functional, and this gives you the action. Okay? And the trajectory can, in principle, be anything, right? It can be anything. It will give you something for the action, and then you will get a number that will appear in the exponent here. Now, if this number is large, okay, so the whole thing is integrated over all the p. Okay, actually, I should say, okay, here, these variables, hidden here in this definition are the variables that we integrate over are p of t and t of and q of t. So actually, what are we integrating over? We don't just integrate over one q and one p. We integrate over all the possible trajectories. Okay, we allow the particle, it's a quantum particle, we allow it to explore all the possibilities for a trajectory. At any time t, it can have some coordinate, some momentum, whatever it is, we plug it into the action and we get a number. We get a functional. Now, And what is going to dominate the integral? Notice that we have an exponent of I times a very big number. It oscillates very rapidly when S is large, right? In a sense. So if we choose a trajectory that causes the action to be very large or to change very rapidly, what it will, this thing will be suppressed because it's an integral over a function that if you take a real part or imaginary part, it's going to oscillate and give you nothing. When is it going to contribute the most?
The minimum.
At the minimum, exactly. And what gives the minimum for the action? The classical trajectory. The classical trajectory will give you the dominant, it will dominate the integral, especially, and now allow me just for a minute to bring back the h bar. Okay, so actually this is what it should be, right? So if we can think of h bar as a parameter that we could tune in a sense, in the limit that h bar is small, there is a very large prefactor here, which makes these rapid oscillations of the S very enhanced, right? So in the limit that h bar goes to 0, the only contribution that will survive is the classical action.
The T-shape left.
No, so I'm saying when h bar goes to 0, which is like the classical limit, what it means is that, of course, h bar has a well-known number, but what I mean by h bar going to 0 is that the parameters that determine the action with the same units are much larger than h bar, okay, which is what you would get for example, if you have a particle with very large mass, right? So it will behave like a classical particle to a good approximation. So in that case, you're going to get from this, although we started from a purely quantum theory, we're going to get the classical, okay?
What you can explain why S in large S is not a...
Okay, so this is a mathematical fact. When you have, so e to the I something, when you have e to the I f of x, okay, this is, and there is a large parameter, okay, suppose you have an integral like that, okay? Mm-hmm. When beta goes to infinity, or when beta is very large, e to the I beta f is a rapidly oscillating function,
Okay.
right?
Mm-hmm.
Rapidly oscillating function gives you a lot of cancellation. So, and in fact, it's going to be dominated by a saddle point approximation. So I don't know if you learned it. Did you study it in mathematics? Maybe it's going to be in mathematical, how do you call this course? Mathematical, there's a compulsory course for theorists at least, which is mathematical methods, it's called. I think this is where you learn it. But in any case, it's a very useful technique in mathematics. But the idea behind it is that when you have an exponential of something that changes very rapidly, it's dominated by whatever gives a minimum to the exponent. Okay? It's very, very intuitive.
But the exponent is a limit between -1 to 1. It says
No,
sine and sine.
no, I'm saying it's an exponent of a function. The function here has to take a minimum.
Yeah, but the exponent, it's sinus and cosine.
That's right, but you have an integral. You have an when you integrate over sinus with very large frequency, you get 0. Or not exactly a sinus, or sine. I mean, when you have a convergent integral, but a convergent integral that what's inside the integral changes sign many times.
And it's cancelled.
Then it cancels and you're left with, and the only contribution you get is from a region in X, if you like, well, this is when you have a one-dimensional integral. Here we have actually an infinite dimensional integral, but it chooses, there is a manifold of P's and Q's where you get minimum to the function in the exponent. That's where you get the main contribution. Okay, that's the intuition. Mathematically, there is a well-defined procedure. Okay? Yeah?
Why to add h bar when you mean when h bar equal to 1?
Yeah, it is equal to 1, so it's correct, first of all, because I divided by 1. But if I, for just a minute, relax this definition of units, in real units, you do have an h bar here. And it's useful to keep it as a parameter if you want to do the so-called semi-classical. What I just described to you is a semi-classical approximation, okay? Which takes the limit h bar goes to 0. But we don't necessarily have to do it. I'm just saying, if you can't solve it exactly, in some simple cases you can solve it exactly. In fact, shortly we'll see one example, but if you can't solve it exactly, one of the approximations you can make is a semi-classical approximation, which boils down mathematically to doing a saddle point approximation. Okay? All right, so, but I'm not done yet, because in this expression, I still have integration over two variables, Q and P. But one of them I can solve very simply. Why? Because the potential energy, I don't know, it can be, I mean, in some cases, if it's 0 or if it's a harmonic oscillator, I can solve exactly. If it's something else, I don't know how to solve exactly. But the kinetic energy is always p squared over 2m. So what kind of integral I get? Only on the p. If I only integrate the p, I will get the Gaussian integral, right? So let me do it. Let me do one step. Inside this integral, I'm only integrating over the p. Okay? And I use the fact that integral dp from minus infinity to infinity of e to the, let's see what we have in the exponent for p. And we have p q dot minus h, right? And all that times I, okay? I once again forget about h. Okay, so I have, let me write it like this. It's minus I. Sorry. Now here I just integrate over one time step. Of course, I have here a product of dpn, capital N times, p q dot minus, actually, wait, I think sorry. that's what I have. Right, okay. I'm forgetting something, times dt. Okay. So this is the type of integral I have to do, capital N times. But it's the same integral every time. And there is also, so here I took the kinetic, only the kinetic part of the Hamiltonian, because the potential energy doesn't depend on P, right? So I'm only integrating the P part of the stuff. And what is this? It's a Gaussian integral. I have a formula for it. So let me write it down. So this is going to be some prefactor. Okay, I also want to keep let me use the factor of 1 over 2 pi here, just for keeping the convention right. And this is going to be m over I dt. There's a factor of two pi. Yeah, that's it. Okay, that's the prefactor. And then I have an exponential because it's a Gaussian integral. The formula that I'm using, let me just write it on the side. Where should I write it? Integral of e to the minus ax squared plus bx is okay, this is the formula that I'm using. You're familiar with it, right? But notice that there's a subtlety, a small subtlety. No, so actually it is allowed to continue it analytically also for the case that A is imaginary, but there should be an epsilon. Let's not worry about it. It is still correct if A is imaginary, okay? Okay, now actually then it will give us a prefactor that has a square root of I, but we anyway don't care about the prefactor because this is something we swallow in the normalization. What we care is about the functional form of the final exponent, okay? So, okay, so this is going to be, let me just make sure that I have the factors right. So it's I mass times q dot square dt divided by 2. That's all. Okay, that's what you get. Which is, what is half m q dot square?
T.
It's the kinetic energy written in terms of the time derivative of q instead of p, right? Mm-hmm. Which is the proper way to write a Lagrangian. So eventually what we're going to get is, after integration over p, we remain with integration over the functional of q of t, where the functional will depend on q and its time derivative instead of q and p. Okay. So let me write down the final result. And then we'll discuss the physics a little bit.
רק את ההמשך, מה שלא מחקת עדיין להשאיר.
Actually, let me, I think I don't need this anymore. So what we get is the following expression. Integral for Q with the constraint that you start from Qi, you end with Qf, and in between you integrate over all the possible trajectories of Q of t of e to the I s, where what is this s? Where s is the integral from 0 to t of L of Q and Q dot. And let's write it explicitly. It's nothing but the kinetic energy half Q dot square minus V of Q, right? T minus V. Written in terms of a Lagrangian language. Okay, so I'm putting this in a frame where I still owe you a definition of the differential. So, what is d of q? It's the limit of infinitely many time steps of a product of sorry, there's a prefactor, so first let me write a prefactor of and then I have a product of EQN. That's it. Okay? Actually, if you want to be really careful, it's maybe from to n, capital N minus 1, because the Q, the final Q is already constrained to be QF. Okay? So these are only the intermediate times. Okay, but in any case, N goes to infinity, so it doesn't matter. And yeah, this is what it is, and it looks nasty. In fact, mathematically, it's very shaky because it's infinite dimensional integral, but really what it means, now let's analyze what it really means, and it's exactly this if you like, I can okay, I can write it right here just to denote that this action is dependent on a choice of trajectories, and you are integrating over all the possible trajectories. Okay? Now let's understand what it means, and it's just what I explained to you before. So you have, this is your system. You start from, at time equals 0, you prepare the wave packet at qi. You put your particle here. You let it evolve in time. This is time. And this is t equal capital T. And after a long time, you ask what is the probability, or actually what is the probability amplitude to arrive to QF at the end. Okay? So I define an initial point and a final point, and in between the particle has to undergo some trajectory. Now, how many trajectories can we choose that go from QI to QF? Yeah, so there are infinitely many trajectories, right? I can choose this trajectory, right? I can choose this trajectory. Okay? I can choose, I don't know, maybe this trajectory. Why not? Okay? And so on. I have infinitely many possibilities. I have no more colors, right? And actually, out of the many possibilities, there will be one particular one. I don't know how it looks because it depends on the potential, but there might be, let me call it Q classical. That's going to be the classical trajectory, the one that solves the equations of motion, which are derived from giving minimum to the action. But in quantum mechanics, the action is a functional of Q of t that can take any value, any trajectory, and the reason that the final result, or if you like, the probability of a particle to arrive to a particular point QF is defined. What does it mean to integrate over all trajectories? For each time step, I'm summing over amplitudes, and they are complex amplitudes. I'm summing over amplitudes that are infinitely many terms, right? So at each time step, the particle can be anywhere, and it gives something to the e to the is. And then I go on and go on, and the final result can be thought of as an interference experiment, because the particle can have multiple histories, if you like. Most of them will not contribute much to the final result. There is one that will dominate, especially when h bar is in the limit goes to 0. But in principle, for a quantum system, this is what happens. This is one way of understanding time evolution. Okay, a quantum particle does not have a well-defined position or momentum at any point in time. It's a quantum particle. And the time evolution, the Schrödinger equation here is buried somewhere. But it boils down to exploring all possible histories or all possible trajectories, summing up coherently their contributions. This is what I mean by there's an oscillating function here that we are summing over, and then most of the trajectories will actually interfere destructively and will give you some contribution from whatever is closer to some extent to the classical trajectory. Okay? But with uncertainty, of course. Okay, so that's the idea. So in fact, the Feynman path integral formulation is bringing it back to the problem of one slit or two slit experiment. Okay, we can, by the way, generalize it to a case where you have two slits and you're looking for what will happen at any point on the screen, right? This is exactly the two slit experiment. And so this is what it is, okay? This is the meaning. And if you can solve this integral exactly, you're done. Okay, now, actually, in the case that you have a free particle, the case where V of Q is 0, is very simple because everything is just a Gaussian integral, right? So you can solve it exactly and find an expression. The final result is less important. You will do it in the tutorial, but the most important is the idea, okay? And let me once again repeat the idea. What was the trick? We started from operators that are non-commuting, but we used the fact that in a time slice that is sufficiently small, we can convert them into numbers, and then you convert the problem of solving a Schrödinger equation, which is an eigenvalue for some operator. You convert the complication into solving an integral of numbers, where you no longer have to keep track of commutators and so on. In that sense, it's very convenient. The price that you pay is that it's an infinite dimensional integral. Okay? But we have a lot of approximation methods how to deal with such integrals, and therefore it may be useful. Okay, so now the last thing I want to do, which I hope to complete today, is to notice, so what I described here, the problem that I solved is the problem of calculating a propagator for a time evolution of a particle, okay? There is a seemingly different problem that by a mathematical trick, you can directly derive from this result. And what is this problem? So suppose the problem I want to solve is not time evolution, but rather I want to do statistical physics of particle. Actually, I better do it for many particles, but for the moment, let's look at a single particle. Let's say I have a single particle, and it lives in a bath with some temperature. There's some temperature, and I want to do thermodynamics, not dynamics, but thermodynamics. Okay. And it's the same quantum particle. It has the kinetic and potential energy. So in thermodynamics, or rather in statistical mechanics, problem. What is the quantity I want to calculate from which you can derive everything? It's a partition function, right? Partition. And let me write it. It's the trace over all possible quantum states of e to the minus beta h. Right? This you are familiar. And here beta is 1 over, I'm sorry that I'm using the same letter. Okay, so okay, let me call it temperature. Okay, because I'm not going to use T, I'm going to use beta. Okay, and here, yes, you're right. So K Boltzmann is also 1, as well as H bar. Okay, let's agree on that. So beta is the inverse temperature. And this H is the Hamiltonian of the particle, and I want to find a partition function from which you can calculate derivatives to find some thermodynamic quantities. Now let me write explicitly what is a trace for a quantum system. It's just the sum over all possible quantum states. Let me denote it by alpha of this thing. Okay? And alpha can be any state. Okay? I can choose a basis of orthonormal state or orthonormal basis. And this is just a definition of a trace. Okay, it's a sum over the diagonal elements, diagonal matrix elements of e to the minus beta h. Specifically, I can choose alpha to be the state Q, right? And then this becomes, okay, so I relate alpha to the label Q. Because it's a continuous variable, it becomes integral over Q of Q e to the minus beta h Q. Okay. All right, so and now my technical problem is how to calculate it. Now I'm claiming we already did it, in a sense. Why? Because if you look at this matrix element, diagonal matrix element of e to the minus beta h, what does it remind you of? It's like the propagator, right?
Yes.
But notice that, yes, so one difference is that, or not a difference, it's a special case if you like, is that Qi equals Qf. Secondly, most importantly, there's no I here. Instead, there is, it's minus beta. So we want to make an analogy with a propagator of Q, I'm using the same notation, so Qi and Qf are both equal to Q. But what will replace what before was the capital T, the time? It's I have to change to change IT to beta. Okay, So this beta, let me write it here. I change IT to beta, okay? What was before IT, and or if I invert this formula, actually beta is minus I t, right? Sorry.
T is minus I.
Yeah, sorry. T. I'm really getting tired. T is replaced by minus I beta, right? So if I already solved for the propagator, I just have to plug in here minus I beta instead of what before was T. And I have a closed expression for this, okay? And then I can do a final step, which is integrating over Q, which is a simple, just one more out of infinite. All right, so this trick, well, basically what am I doing here? So I'm going to, basically what does it mean to change time to some imaginary, some I times the inverse temperature? And this inverse temperature is a kind of imaginary time, okay? If I'm looking at it like this, so beta, the inverse temperature, is an imaginary time, and it's given that name, okay? So we use here a transformation that is called a weak rotation. It's a rotation in the complex plane, if you like. If we think of time as a mathematical variable, which lives in a complex plane, we can rotate it from the real axis to the imaginary, okay? Just formally, and it's the same weak of the weak theorem. So weak rotation is defined exactly like that. You change, you define tau. Actually, let me just make sure I have the signs correct. Yeah, that's correct. Yeah, so I'm basically doing this. I'm changing T to minus I tau. Tau now will be the index of the imaginary time that goes between 0 and beta. Okay? So we can think of conceptually, eventually in the expression for G, we have an integral over the action, right? And the action is an integral over time. But if we do the weak rotation, change variable from T to tau, you will get an integral over tau. Okay? So you have your space variables, and now imaginary time axis, and the expression that you get is, it can be thought of as evolution in imaginary time from 0 to beta. Okay? Actually, what happens at 0 temperature? So if I'm interested at 0 temperature is beta goes to infinity. So the upper limit will go to infinity. Okay?
Now minus?
we'll see how it, I mean, I still didn't do the conversion properly, but in the end, there is a variable. We're going to write everything in terms of a variable tau instead of t. And this variable changes from 0 to beta. Okay, and tau is the imaginary time. It's really the name. Okay, so it sounds very fancy and, you know, but it's really just a mathematical trick. But it's useful to develop intuition. In a sense, we can think of this thermodynamic problem as some kind of evolution, and the time variable, okay, it plays, all the quantum properties will be coming from the fact that there is a non-trivial dependence on this imaginary time, okay? So I think we should probably stop here. Let me do. We still have 2 minutes. I think I can finish and get to the main result. So let's just write this. Okay, let's just write it because we already know the answer. We know the answer. So what I'm saying is the partition function is an integral dq of g of q minus I beta, and this thing is this thing we saw that we can write as okay, let me write it like this because we are going to change q of tau to q of t to q of tau, and there is some differential times e to the I is, but the integral is from 0 to beta of minus I d tau, okay, of L of q of tau, which we still have to find. But notice that here I have I times minus I, okay, which gives me d of q of tau e to the plus d tau L of q of tau, which I still have to write down, okay? But what is it? What is L? L is, in the original variables, it was half m q dot square minus v of q, right? But q dot is dq dt, right? But I want to change variable to t goes to minus tau. So it's minus d dq to d I tau, right? Now, but here I have q dot square. So q dot square is, there will be an I times I is minus 1, so altogether I'm going to get dq d tau to the power 2. Sorry, with a minus sign. Sorry, all right? Because of the I get minus dq d tau. Actually, let me write it as, sorry for being a little sloppy. Let's just use this notation, okay, for the time derivative, shorthand notation. Okay? And notice that when I plug this into the Lagrangian, I will have minus half m d tau q square minus v, so there will be an overall minus sign. And altogether, what I'm getting from this is e to the minus s Euclidean. It's called a Euclidean action because what is S Euclidean? Actually, let me write it like this. What is it? It's an integral d tau from 0 to beta of half m d tau q square plus v of q. Okay, and it's called Euclidean because it's the kinetic plus potential and not kinetic minus. So the time and space have the same sign. It's like Euclidean versus Minkowski in relativity. Okay, that's where the name comes from. Yeah, and that's it. And now I forgot one more thing, that here the constraints on the limits of the integral are that q of 0 and q of beta are equal and equal to q. So it's periodic boundary condition. Okay, so actually it describes a trajectory that closes on itself, if you would like to think of it as a variable. Okay, so let's stop here, and next week we're going to see how to extend this in many